going to have a look at, well, Fibonacci numbers, how they relate to the three Great Pyramids at Giza, and also how they will bring us to the Nonagon, or the nine-sided shape, or the nine-pointed star, which is technically impossible to draw perfectly with compass and straight edge, but we can do a very, very close approximate. I stumbled upon this looking into the pyramids, and I think this is actually the most accurate compass and straight edge Nonagon that is known out there. I don't think it's been published anywhere else. I tried to find it, I couldn't see it. Maybe perhaps it could have been, but either way, this brings us very nice knowledge connections to all three of the Great Pyramids, Fibonacci numbers, which of course relate to the golden section, just the inherent geometry of things, and again, phi ratios, as they are so wonderful. I'm going to begin with the construction line, and it all should work together. So if I probably should have room, but for instance, this is part of, and I'll insert a graphic here, but we have the three pyramids at Giza, the Menkaure, Khafre, and the Great Pyramid. Now these first two, the Menkaure and Khafre pyramid, the basic plan emerges from this Fibonacci spiral, and then we'll go to the Nonagon, and that gives us the ratio for the Great Pyramid. And so I have room, make sure I'm in camera. Okay, I've done a construction line. I'm going to be using two compasses because one I want to adjust, and I want to keep this one at the original setting. So begin with a Vesica, two circles, the center of the second on the edge of the first. Now we have, from our construction line, now we can cut down there and create four 90-degree angles. Place my point, and so that will just be a construction line, but now place the point at the center. Now the Vesica Pisces is 1, 2, 3 wide and 1, 2 high. So we already have a 3:2 ratio, and that already gives us the basic design for the Khafre pyramid, the second of the three Giza pyramids. So compass in the center. Now on the edge of a circle, I'm going to do the same. I'm going to draw a small arc and draw an arc again. You want it directly above. Do the same on the other side. What we're doing is we're going to draw a rectangle around this Vesica. And with that, now I put my compass point at the center, find the edge of the circle. So now I go to the top, there in the center, mark again on the other side, and do the same at the bottom. Now we have the 4 points of the corners for the rectangle, 2:3 ratio rectangle, which encloses the Vesica 2:3. And actually this line I'm going to carry on up to the top, markers going. Do the same with this line, and I'm going to carry it on up further. It's a little bit, okay, I'm just brushing, but if you take your time, use the finest point that you can, but with the numbers we can demonstrate the accuracy of the Nonagon anyway. And again, I'm going to carry that line out. Let me get rid of this marker. And I'm carrying these lines on because they're going to be helpful in the construction of the Fibonacci spiral. Okay, so we have a 2:3 rectangle, 3 wide by 2 high. Change colours. And we already have the Khafre pyramid, that central pyramid that still has its capstones on the top. So there already is your Khafre pyramid, which is 411 cubits, Egyptian royal cubits wide, and 274 Egyptian royal cubits high, 2:3 ratio. And from the Vesica, we have the Khafre pyramid. Okay, now I'm leaving this is still at the original setting, because now I want to use this to help with the Fibonacci spiral. So I'm going to mark each one of those sides. And so since the Fibonacci is 3 wide, now I have 1 by 2. So what I have here is a square, and I have a 1 by 2 rectangle. I'm also going to draw a line here. So now I have one square, a second square, and a third square, which each of these squares is 1 by 1. This is a 2 by 1 square. Okay, so because we already have this circle, let me change the color, because now we'll be drawing the Fibonacci. What color would stick out better? Go for a green. Just make sure my point of the marker is right. Okay, so I draw. Now we have a quarter circle. Now the rest of the Fibonacci spiral is just a series of creating squares and quarter circles. So that's our first quarter circle. Now I don't need to, and Fibonacci numbers, 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 13 would be the next, but we only need here because we're working towards a 5 by 8 rectangle. So we have a 1 by 1 square, 1 by 1. Every time you want to extend the Fibonacci spiral, you find the longest edge of this point. It's a square, so they're all the same, and then you extend it by a quarter circle. Let me get that accurate. So again, I've just used another quarter circle, and these are already the lines in the circles inherent in the Vesica. So we have a 1 by 1. Now we have a 1 by 2 rectangle, 1 by 2, and now we need to make a 2 by 3, and so where I ended the last spiral, now I adjust my compass to that point, and let me be more accurate with that. It's just another quarter circle. And you can already see the snail spiral, the Vesica spiral emerging. Well, I'm not sure if my compass will extend that wide, but so now we have 1 by 1, 1 by 2, and now a 2 by 3, which is the Khafre pyramid. And now the longest edge of this rectangle is this. So now we just draw another quarter circle. And that's why I left these extension lines out to help with that construction. Okay, so now it's just another quarter circle. And if you're drawing a properly, you would also use that to mark. So now we have another square, but it's not necessary for where I'm going. And now my compass won't open that large. I should have, yes it will, but just inside. Okay, so quarter circle, we extend it on the longer side. Now the longer side of this rectangle is here. Okay, so now another quarter circle. And so now we have 1 by 1, 2 by 1, 3 by 2, 3 by 5, and now a 5 by 8. And now I draw the enclosing rectangle around there. So just hand that line out. But now what you have is a 5 by 8 rectangle. Caffrey pyramid is a 2 by 3 ratio, 3 wide by 2 high. Menkaure, the smallest pyramid, 200 Egyptian raw cubits wide on the south and north base, and it's 125 high, which gives it a 5 high by 8 wide. And well, now I just need to, what I want to do is now draw the the Menkaure pyramid. So I need to find the center point, so we can just bisect that line. Actually, I'll do it on this line. You should bisect it top and probably bottom if you do, just to be super accurate. But just extend the compass anywhere over halfway. Okay, actually, sorry, I should do it over here. You can just eyeball it to get halfway. And if I go to the opposite side, now I've bisected that line. So this would be exactly halfway between here and here. I could just mark that point. Now from the corner to there. And that gives us the profile of the smallest of the three of the Menkaure pyramid. 200 Egyptian raw cubits wide, 125 high. Caffrey pyramid, 411 by 274 high. Now, of course, they're not in scale, but Fibonacci numbers 1, 1, 2, 3, 5, 8. Is that now we've created a 5 by 8. Probably do it a little bit larger, but we have the three. I'll put an illustration here, but we have the three Giza pyramids: Menkaure, Caffrey, and Khufu, or the Great Pyramid. The Menkaure, the smallest of the three, is 125 Egyptian raw cubits high, 200 Egyptian raw cubits wide. That's this triangle here. That's the smallest of the three, the Menkaure pyramid, which is a 8 wide by 5 high. The Caffrey pyramid, the one that appears to be the biggest, but it's on a raised platform. It still has the casing stones at the top. That's 411 Egyptian raw cubits wide at the base, 274 high. So it's 2 high by 3 wide, these Fibonacci. So that would be the profile of the Caffrey pyramid. That's the profile of the Menkaure pyramid. We get these from the Fibonacci numbers. But then we have the Great Pyramid, which is 280 Egyptian raw cubits, 280 Egyptian raw cubits high, 440 wide. That's so 7 high by 11 wide. These are Lucas numbers, by the way. So you have Lucas 1, 3, 4, 7, and 11. I'll put a link in the description how the Fibonacci spiral and the Lucas spiral bring you to the same golden number eventually. But this 5 high by 8 wide, the Menkaure pyramid, the rectangle here. So what I've done is I've just drawn a 5 by 8 rectangle, and we're going to draw the Nonagon. We're going to create a Nonagon that is toot my own horn, but seems to be the most accurate Nonagon using purely compass and straight edge methods. And we get that. So this rectangle is just 10 centimeters high by 16 centimeters wide, therefore 5 by 8, just like this Fibonacci spiral we've got here, which is a Menkaure pyramid. And so the Menkaure pyramid would be the triangle in here, and then I've just simply drawn a circle centered on this corner. So now if I draw a line that's a diagonal, and I want to use again, if you're drawing this, you want to use the finest point as what's possible to get this as accurate as you can. But if we draw a diagonal through there, I'll put a card here. You can use trig, double check it, online right angle triangle calculator. We have a right angle triangle here. Let's call this angle A. Angle A would be 32.0053832 degrees. So the 5 by 8 rectangle created by Menkaure pyramid is 32.00583, etc. Now we can just use the laws of Euclidean geometry, and now I'm going to bisect this angle, so I'm going to cut it in half. This you can do with 100% perfection using the Euclidean geometry. So I'm just going to draw an arc, and then I'm going to use this one. Now I just need to set the compass anywhere over halfway, and draw an arc. Do the same at the top. And now we've bisected that angle. There's my final point. Now a problem with drawing such as this is that the thickness of the pan and just, human inaccuracies to get it perfect, but mathematically speaking, we're going to use that. So if you do draw it, you can test it on GeoGebra or such programs to be sure. So now we bisect that angle, and therefore angle B should be, by strict definition, 16.0026916 degrees. And now I'm going to bisect that angle one more time. Now, technically speaking, the Nonagon is impossible to draw perfect with compass and straight edge. But again, it's going to, as far as I know, it's the most accurate one, and I got inspired to find this by, again, studying the pyramids in ancient architecture. Now this would also relate to the dodecahedron, so 32 degrees. I have a dodecahedron here. Now, if we lined it up so we have the axis of going across the middle, so it's perfectly lined up, if I rotate this 32 degrees, I should get the axis going right through the middle of this. So there's an application to the dodecahedron. Also the Sphinx, there are various analysis of the Sphinx face, and they've noticed a 32 degree angle in the face of the Sphinx, but I'm not too sure about that. But anyway, so we've bisected angle A, and now we've bisected angle, so we get angle C. By strict definition, if we draw it perfectly, at 8.001345 degrees. Now I'm going to use the circle, because now we have all the points we need, because a nonagon is 9-sided shape, a 9-pointed star. 360 degrees divided by 9 equals 40 degrees. And if I add 32 plus 8, I would get 40.006729 degrees. So less than 7/1000ths of a degree. and that is with compass and straight edge with the most steady hand, the most finest point. If you can, you know, like that's 7/1000ths of a degree is way beyond what a non-superhuman could achieve in this level. So, oh, that would be, if I add 32.055 plus 8.001 degrees, I want to get 40 degrees to be a perfect nonagon. Using this construction, I'll get 40.0067, which is 7/1000ths of a degree. Again, essentially impossible for a mere mortal to achieve this level of perfection, no matter how fine your point is, no matter how much time you take to get this accuracy. But so angle C plus angle A will give us 40.006729 degrees. And so put my compass point on there. I adjust it to get as close as I can. And the problem with this compass and straight edge drawing is that any minor error grows every time you add to the construction, and again, to get within 7/1000ths of a degree is, well, again, very, very hard. Now, the shadow is confusing me a bit. Yeah, that should be. I want to get my point there. Okay, no, that's why the shadow of the point is. Okay. Give me a moment. I'm going to try to get this as. That should be it. No, it's still a bit big. That should be it. Okay, so if drawn properly, this angle D would be 40.0067 degrees. Now I can set my compass there, and okay, now we can just chase that circle around. My hand out of the there you go. It's even would be closer, properly speaking. Again, the thickness of a pencil, shaking hand, even the vibrations of traffic is going to affect you if you're trying to get within 7/1000ths of a degree. So now we have 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've created nonagon, and that final angle, so if we had a perfect nonagon, that all the way around would be 320 degrees. Again, it's actually 320.05383 2 degrees. So it's less than, the final angle chasing it out would be less than 6/100ths of a degree. You've drawn a perfect nonagon using the compass and straight edge method. Technically, not mathematically super accurate, but again, in the human real world, if you can get anywhere close to that angle in engineering, you're going to be a rock star. So now I've just used a protractor to draw these out, because there's another aspect here in regards to the nonagon. Now, I'll just draw them freehand, but let's say you want to, you draw a hexagram, or as what most people would recognise, a Star of David. That's 2 equilateral triangles overlapping. You have to draw 2 triangles to do it. There is a way to do it with one line, but it doesn't create a regular shape. However, that's 6 points, so it's an even number. However, if you draw a pentagram, for instance, which is 5 points, you can do that in one line. So the nonagon, I've just marked out the points. It follows that rule because it's 9 being an odd number. So if I just follow this around, and so again with one, without ever having to remove the pencil or the marker, you can create this 9-pointed star. Let's move it. Okay, so like the pentagram, you can do it with 1 point, but the interesting thing about the nonagon, well, you can also create a series of overlapping equilateral triangles, and I'll put an image of Kershaw here to show you what I mean. So if I start at 1 point and I skip 1, 2, and then I go to the third, skip 1, 2, go to the third, and then come back. Now we have an equilateral triangle. If I repeat the same again, let's get 1, 2, and this over here. So now we have another equilateral triangle, and then with the 3 remaining, we have a third equilateral triangle. So it's nice that this nonagon sort of is works in both worlds, both the odd and the evens, in regards to making the stars from there. So we have 2 variations. So this is the one, for instance, used in the illustration by Kershaw, which has the 3-4 triangles and the 6/5 ratio hidden in plain sight, so to speak. But now we can do a nonagon, so a 9-sided, and we just go from point to point. But that's where this, some interesting connections come in. Because now we have the center point, so the defining angle of a nonagon is 360 divided by 9, so that's 40 degrees. But we also have the interior corner angle, that's 140 degrees. Therefore the exterior corner angle is 220 degrees. Now the common divisor between them is 20, so in other words 140 divided by 20 is 7, 220 divided by 20 is 11, and that is the ratio of the Great Pyramid, which is 280 Egyptian royal cubits high and 440 Egyptian royal cubits wide, which gives us the pi and phi ratios in there as well. So that's a nice link. So from the Khafre and Menkaure pyramid via the Fibonacci spiral, we can create a nonagon which is so its accuracy is above what's achievable with compass and straight edge. And the nonagon leaves us this important esoteric symbol, both this but also the crossover between the 5 and the 6 type of pattern, where it's one line or overlapping regular polygons such as a equilateral triangle. And then of course then we have these. Now is another interesting feature is, so 360 degrees, each degree is broken down into 60 minutes, and each minute is broken down into 60 seconds. Now we use decimal, but the old school way was minutes and seconds, exactly the same on the clock, where 1 hour is 60 minutes and each minute is 60 seconds. Same principle in old school navigation. So 40 degrees is equal to 2,400 minutes on the compass, or 144,000 seconds. So that's one of these key ancient numbers, east to west, modern and old, 144, especially 144,000. I'll put some cards up about that. Now 140 degrees equals 13,200 minutes. Now that's half of that is 66, half of that again would be 33, but it's also equal to 504,000 seconds. Now 504 is nice, but okay, I'll put up something now about 5,040. And 220 degrees is equal to what's that, 1,200. Did I do that right? Sorry. Ah, no, forget what that. I've lost my mind. That's not 1320, that's 8,400 minutes of a compass, and this one is 13,200 minutes, or 792,000 seconds of the compass. Now each one of these is super cool. Now I'll put up some cards and images now. Five thousand 5,040. And all that's related to 792. And of course the Great Pyramid ratio, and also the
Caffrey and Mancaro pyramid ratio by the Fibonacci. I'll also link in the video in the description how I use this same, beginning with the Vesica Pisces here, how I also get to the 7-11 ratio via the Lucas numbers. And by drawing a Lucas spiral, we also get the Great Pyramid 7-11 ratio. So the Nonagon from the Fibonacci, and again, as far as I know, as I could find, this is the most accurate way with just compass and straight edge, and so accurate that it goes beyond the limitations of using tools such as these. But mathematically, geometrically speaking, it is not perfect. It is 7/1000ths of a degree from accurate. And yeah, Kershaw, the 9 connections as well, Fibonacci, Lucas. Links in the description. Cheers and have a good one.